Our first speaker today on low power is Gabriel Chidolue from Graphics, who's a verification technologist. He will be speaking about successive refinement and methodology for incremental specification parameter using UPF.
Good afternoon. My name is Gabriel Chidolue. I'm a verification technologist, Graphics, focused on low power verification, amongst other things. I've been working on low power for the past 9 years now. The very early days, we actually came up with our own format, and I did participate in a minor role in the early days in the advent of UPF in the Accelerator working group. I didn't pursue that any further. Anyway, today, why are we here? Well, we're here to look at UPF and how the methodology has been evolving. Well, the UPF standard itself, as you know, is evolving. There's been a lot of changes. I'll go through a timeline. The best practices for low power design and verification is evolving. Why? Because the designs themselves are evolving. And there's actually a need, if you look back at, let's say, 8 years ago, power in particular was considered a back-end task. And around 8 years ago, the UPF and the other methodologies or other ways for specifying power intent tried to bring or pull that verification and design task forward to be considered early as well. Well, things have moved on since then. Now there's a need to provide a methodology or a way of capturing or doing a lot of the work, the design work and the verification work even earlier as design complexity increases and as intent that's captured in IP gets pulled into SOCs. So that the methodology or the right methodology has to take into account IP, usage of IP in different contexts. The IP designer might not necessarily know how the IP is going to be utilized, but there's a lot of knowledge that they have about the IP. They can specify or say things about the IP that might be useful or would in fact be useful when the IP is used in many different power architectures or contexts. The methodology has to enable verification in all the different forms. It has to allow for the designs to be easily retargeted to different technologies. Different technologies enable different types of architectures and strategies. So the methodology has to be cognizant of that and be flexible enough to allow the designers who are doing the work up front at the RTL to have that flexibility to target different types of technologies. It has to simplify debug. That's another challenge that we see in the industry. Being that power is a system level concern, it tends to be done right there once you put in the entire SOC together. And that proves to be a big challenge because you have a massive design ready to contend with. Now you're adding the power architecture on top of that, which comes with its own inherent logic that has to be all verified. So you need a UPF strategy or UPF methodology that allows you to easily debug the design, the complex design blocks, the complex architectures that you want to introduce. Ultimately, you want to decrease risk. So we've been working for the past 2 years now with ARM on this idea of successive refinement that takes a very IP-centric view. So this talk I'm going to be doing today is based off of what we presented at DVClub in February. I've updated the slides here with some of the results that we've had since February, around the that time frame. And at DVCon in Europe later on this year, we'll be talking a little bit more about additional work that we've done, taking into account implementation challenges that we faced as we try to carve out and follow a bottom-up implementation flow while still providing a successive refinement approach for describing the UPF. So what's UPF? It's a standard that itself has been evolving, starting with the Accelerator version, commonly referred to as UPF 1. Then IEEE took over, and then you have the UPF 2.0 that was ratified in 2009. 2013, you have the 2.1 version, And there was actually an interim version in 2014, not actually what's happening now is that we're going through ballot of the UPF 3.0 version. That, if all things go well, that should be released around the early part of next year. So it's based off of Tickle. It's allows you to provide the whole point of making a Tickle so that tools can take the information out of the UPF and then use that to augment the design, to add the structures. So VHDL designs, Verilog designs, system Verilog designs, they're all supported. And then in the UPF 3.0, when that comes out, System C designs will also be supported, in the sense that, well, I'll talk about that in a few minutes. What do you do with UPF? It's used to capture the power. And in this case, it's all about power management for controlling static or moving power. It's also used to optimize power consumption. It's used by the verification tools to verify the different power states that your design should potentially be, interaction between power domains, interaction between power states, and to make sure that you've provided that the designer has created an architecture that has adequate protection across the different power domains that we partition. Different types of verification tools are supported and can read UPF, including emulation, simulation, static and formal verification in various different forms. And I'll talk in a few minutes about how you could leverage different types of static in a few minutes. And then for implementation, your DFT tools that will insert test logic, synthesis tools that will actually transform the design will read UPF and then use that to create the appropriate structure that actually result in likeness, all the way through to place and route as well. In 3.0, one of the biggest things that's being done in that standard is to allow us to go right up to the architectural stages, where you're still designing and working in System C realm, so that when you're working in that realm, you can begin to understand the impact of partitioning your power into specific domains to see whether there's actual benefit in that particular partition that you've come up with. So here we're looking at simulating with a high-level model and understanding the impact from a power point of view that those models might bring, depending on the partition architecture you come up with. So that's a big amount of work that's been added in the UPF 3.0 standard. Okay, so let's have a quick recap on some of the power management concepts. Well, first is for power domains. Those are the individual or independently managed blocks, if you like, of a typical SoC. These blocks will typically have different types of power strategies associated with them. They could be put in some sort of operational, non-operational bias mode. They may be operating at different voltages, or they may be shut off completely, while other parts of the design might be operational. When you do that, when you shut parts of the blocks off, there might be need to specify state retention, so that you could, when you want to wake up that block, you can wake it up much faster. Some essential state has been specified, or you have to take up. In order to protect different blocks that might be on or off relative to each other, there will be need to specify isolation, so that a driving block that is powered off, it has its outputs clamped to a valid value that protects the downstream or receiving node. And then if you have power domains that are operating at different voltages, then you have to do some sort of level shifting to translate the voltages so that the receiving end sees the correct and legal values that represent on the okay, so these are the concepts that you typically find in any power managed design, and it's typically captured in the UPF. In the UPF one flow, there you would have a design, the RTL, and effectively a monolithic UPF file. As I said, this is something that was done. If you look at going back about 9 years ago, what we had was UPF1, and the only way you could do things was really to consider power at the system level So you would have a UPF that had a system level view that captured these concepts, if you like. That UPF and the RTL will be taken into synthesis after verification, where you check that your legal power states have been gone through and you transition through your legal power states, and to ensure that the design works, whether or not you count the blocks into different states, bias or off or whatever. And then once you've gone through implementation, you could use simulation to check the net list and the accompanying UPF that might have been transformed through the implementation phases. Or you could use logic equivalency checking to ensure that the output of the implementation honored the UPF strategy that you specified upfront to the output. So here you'll be using UPF and RTL and checking that against netlist and UPF. Other verification capabilities that you might want to throw at this would be emulation, especially when you see that in many cases the power control logic itself is usually under software control. It might be necessary to run application software or driver software or OS software that has the power management concept to make sure that the hardware software interactions are actually verified. Okay, so what was the issue with this flow? Well, in this flow, you had to bring in all the implementation detail before you can even do the first level of verification. Given that the designs are getting bigger, this meant that you had to wait to the point where all of the information was available, which could be late in the design cycle. If you look at it from an IP provider's point of view, one of the problems here is that it might be that packet technology information is not known. The IP deliverer or the IP provider knows a lot about the context in which the design could be broken. It might be that the end user will take the piece of IP and decide to break up the IP into power states that are not legal or not supported by the IP. Or they might be attempting to break up the design into partitions that were not really intended to be partitioned in that way into power domains. These various challenges that meant that you could end up taking assumptions that have to be redone later. Okay? In some cases, it would impact, it could be that you have to wait so long that by the time you got to do your verification, it was quite late in the cycle, so you end up doing very little or less rigorous verification. So these were the issues that ARM in particular faced as an IP provider. They had quite complex IP, which end users might try to break up in ways that were not supported by the IP itself, resulting in all of these types of issues. And it's really what gave rise to this work on successive refinement. So what's successive refinement? Well, it starts with the IP creator. The IP creator effectively creates IP, RTL source. It's probably a configurable IP so that it can fit in multiple different contexts. And together with this IP will go what's called a constraint UPF. This constraint UPF is effectively the IP provider saying, if you're going to use my IP, this is what you're going to be able to do with my IP from a power management concept point of view. Okay. The IP licensee will take the IP and this constraint UPF, and he understands the use, or he or she understands the use case for his particular SoC, and so he's going to create all the power domains, the isolation strategies, and so on. All of those things that the IP user creates have to honor the constraints that have been provided by the IP provider. What's also interesting here is that what the IP provider is taking, was given to the licensee, is technology independent. Also, when the configurator gets to put this whole initial architecture in place, they don't even need to consider at this stage the implementation detail. That means that verification can start much, much earlier in the flow. Once this package of RTL, configuration UPF, and constraints has been verified, then you can add the implementation detail. So implementation details, we'll talk about what those things all contain. And then it's at this point that you can go in and do the implementation. So place and route, synthesis, place and route, DFT, while also verifying that implementation UPF and the constraints and the RTL. So let's look into a little bit more detail at what these UPF files contain, starting with the constraints. So the constraints contain the power intent from the IP point of view. Bear in mind the IP is going to be configurable. Bear in mind also that the user may not necessarily choose to implement some of the features that the IP provider has said that will be that can be done with that IP. So there has to be flexibility in the way the constraints are specified. In any case, the kind of things you can do will be in the constraints is specifying the power domains, the smallest level of partitioning that you could potentially do with the IP, the fundamental states that the IP supports, isolation constraints, and retention constraints. These form part of the source that gets delivered with the rest of the RTL. The configuration UPF takes this constraint and then adds on top of it maybe composite domains, because the configuration person might decide that those blocks that have been partitioned are too small and they want to bring that back into a composite power domain. That's allowed. They will now specify power sets. So this is an abstract definition of the power distribution. Power states using logic expressions. So here you're just talking about the states on and off of a particular supply set without necessarily saying anything about the underlying voltages, which is technology specific. And then the isolation strategies and retention strategies that honor the constraints. And then the tools themselves will then check the constraints against what's been specified to ensure that they're consistent. At this stage, you can do early verification using either static checking techniques or even dynamic simulation. Once this is verified and they proven that all the legal states can be reached and that the isolation strategies are all working correctly and interactions between states are fully verified, then you can add the implementation details. So the implementation will be UPF will contain technology specific detail like the power switches, supply nets, association of supply nets to supply sets, and then supply expressions, which brings in the voltage information into the equation. And here too, verification can be applied while also taking that whole combined RTL constraints configuration and implementation UPFs into the implementation tools. All right, so let's have a quick look. We have a simple design here. I say simple, it's not that simple. I have a Cortex, configurable Cortex, MPCore, as the IP that we're going to apply successive refinement to. So the rest of the presentation is just going to show how we can partition and create constraints UPF, and then when we get to use this IP in a particular context, how we create the configuration UPF, eventually how we add the implementation detail. Okay. So as you can see, there are a number of power domains. You've got the topmost PD Cortex power domain. You've got the PDL2 that has all the RAM that belong to the cache. Within the Cortex, you also have the CPU core. The CPU core is divided into two power domains. The PD CPU for everything except the floating point unit, and the floating point unit has its own. For the PD CPU and PD SIMD power domains, those are going to be configurable depending on the number of cores that a particular user may choose to have. Okay.
So the first thing we have to do in the constraints UPF is to define the atomic power domains. And I'll explain what that means. Then we define our retention constraints, isolation constraints, the fundamental power states that the IP supports, any abstract retention states, and I'll talk a little bit about why we chose to have retention states defined here, and then any power state constraints that might be necessary. So the bottom line is that the constraint UPF decides or describes what can or cannot be done with your particular IP as you configure it for your own system. So at this stage, that UPF is pretty much, if you like, it's like a template. It's the way to look at it. The constraint UPF is like a template that affects checking later on. So for this design, let's look at what we could do. The PDL2 that contains the RAM, we'll put it in one power domain, and that we'll call an atomic power domain. It's called an atomic power domain because what you're saying to the user is you cannot break that power domain, that particular design hierarchy, or those sets of elements in the design into any smaller power domain. You couldn't take, for example, the L2, the different L1 caches and stick in another power domain. The tools will tell you, no, you already have these elements as one entity. They have to become one per power domain. That's the smallest level of granularity of power domains that you can have. You can always combine them back up to bigger domains, but you can't break them. That's the meaning of atomic. And the same goes for the SIMD unit, the CPU, and then the Cortex. There are a couple of new commands here that are based off of UPF 2.1. The atomic is a UPF 2.1 language feature. And right at the last one, where you create the power domain for the cluster, where you have dash element dot. That's also new in UPF 2.1. In UPF 2.0, you would have said something like include scope to add everything in a particular scope into a power domain. Okay, and then you will go to specifying retention and isolation constraints. So these are constraints because what you're saying here is if you are going to retain any parts of this design, then these are the things you must retain. So that's what this is saying. In the case of the retention, you use this command called set retention elements. And you give it a name, and you give it the elements list. In this case, we've given it an instance. So what we're saying is if the user is going to retain anything, they cannot retain portions. They must retain everything that's specified within UCA CPU 0. Because otherwise, if you retain only subsets or portions, the design might not function correctly. And that's the information that's being propagated. And tools can check this to ensure that when you're doing the retention, that you're retaining at the right level. Okay. Similarly, for isolation, you use set port attributes. So with use of set port attributes, what you're saying here is that if you're going to, if these blocks fall onto a boundary of a power domain, then this has to be the clamp value to use. So it's very much a constraint there to be used by the tools to make sure to check. The other thing that's interesting is you can see that what we've done on the top is to specify, so what you've done is to use the top to specify a general scheme, and then right down here we've called out a particular port and said for this particular port we want a clamp value of 1. Okay, and then we define the supply power states, the fundamental states. So for the PDC SIMD domain, we have 2 states, running and shutdown. And we define them in terms of the primary supplies for that particular power domain. And then later on for the power domain, for the primary supply itself, we define on and off with sim states, normal and corrupt. One thing we have omitted here is that we have no logic or supply expression specified. That is information that the IP user has no knowledge of, or the IP developer in this case has no knowledge of this information. That will come once it gets configured. And then for res, an optional state that we use dash update. And this is going to be, you'll see the use of dash update because that's the whole point. This is the whole feature or capability within UPF 2.1 and 2.0 that allows us to do this successive refinement, use of dash update. So what we've done is to add a red state with no other additional information. This is an optional state. The user might choose not to use it and just mark this state to be illegal for their particular context. Okay. And then for the rest of the system, we describe the power state dependencies. So we saw that for the PDU SIMD, we had run state. Now for the CPU, we can define its own state in terms of the power state of the domains that we described earlier. So here's a case where we're saying for CPU 0, run, it means that its own primary supply is on and the PDC CPU is also on. So that's how you go about creating the dependencies, if you like. And similarly for Cortex, we do a similar thing. It's in run state when its primary supply is on and the L2 is on and the CPU 0 is on. We can also describe specific illegal states, and that's what we've done here. We've said that you cannot have a case where primary is on, L2 is on, is running, SIMD is running, but CPU 0 is in retention. Such a state is illegal, and you mark it as such. And if in your case you can also say that everything else that you haven't specified is illegal, and that's done by using this dash complete. When you use dash complete, it means that only those things that you've specified are the legal potential states that the system can be in. Okay, so the configuration UPF would first load these constraints and then add the actual things. First, it defines the control inputs, the things that will actually do the controls, because that's what the configuration person knows about. He knows where the power management block is, he knows where the signals are, he knows how the rest of the system is going to fit in the context of this IP. Right. And then so things like the control inputs, retention strategies, those will all be, the real strategies will be defined, and then you will update the power states and the control conditions. Then any refinement of power states will also be done at this stage. So let's have a look at the block diagram just to illustrate. The controls will be added. You don't need to modify the design to add these. You would use things like control logic port to propagate these controls to where they're needed in the design. Retention strategies will be written, and they will take advantage of that set retention elements command. I'll be verified against those. Okay. Isolation strategies will also be written, and what the tools will do will be to check that this clamp value here specified is honored or honors what's been set with the set port attributes in the constraints. Earlier on, we defined fundamental power states. Those will now be refined because now you have the control logic. You know where the controls are coming from. You would refine with dash update to add the logic expression and the controls. Okay. And the same goes for the updating of the retention. If you do use retention, then you will create a retention supply and then update the expression to update the CPU retention power state to say what the SIM states for that particular supply set is. And then also for the power domains, you would do the same sort of refinement. Okay. So, and what if you wanted to even do further refinement? Well, that's also possible. So you use dash update, and then you specify additional states like sleep and deep sleep using the earlier states that you created. So in this case, rect, and maybe logic and a logic expression. So this particular one here will probably be a signal in the design that indicates going to deep sleep. Okay. So this is what it would look like pictorially once you're finished with the configuration of a particular IP within a system context. You'd have the constraints, you've got the configuration. Now you can do verification. with state-based logical verification. This is technology independent. You could also apply static checking at the stage as well. And typically the kind of things you're going to be looking at will be making sure that you're using the components in the right way, the IP are configured in the right way within the context of that particular power architecture. Interface logic are all working okay. Dependencies are all okay. And your power controls are working okay. So at this stage, you don't have the implementation information. So once you're finished with this verification, this is where you add the implementation. So you load the constraints, you apply the supply network, define your power switches, update with the supply sets with the supply expression, and then connect the supply nets and supply sets, and then specify any other technology information that is needed. So let's quickly just show you pictorially what that will look like once you're done, because most of this is just using pretty much what we saw earlier on and adding information using dash updates. Right, get to here. So this is what it will look like once you've added the technology specific information, notably the voltages, the switches, and associating and extending the power supply, the power states to include this voltage information. Okay, so now you can drive implementation tools and also do some more power verification, taking into account voltage-based simulations. Okay. So to summarize, successive refinement basically gives you a clear way to communicate, or a clear mechanism of communication between the IP provider and the IP configurator and system integrators. It allows you to reduce risk, if you like, because now the IP provider is giving you clear communication as to how that particular IP could be configured in its power architecture point of view. Allows for separation of logical from implementation. Means it can debug easily because now you've got this logical stuff that you can begin to verify at a logical level. And when you find a problem, it's easier to know or easier to debug as opposed to when you have this when you have all of this information all in one file, if you like. It's easier to retarget because now you've separated the logic from the implementation. So once you verify the architecture, logical architecture, you can easily retarget to multiple different technologies. Okay.
Okay, thank you very much, Gabriel. Thank you. I think we do have time for one question. We've got 4 speakers, so we're going to be strict on time today. Is there any questions from Bristol? Any questions from Bristol? Sure. Paul Bailey.
Just wanted to ask, since successive refinement's been around since 2.0, are you seeing many IP providers or SOC teams using this methodology as opposed to the traditional detailed description in UPF right from the start?
I think it's fair to say that, yes, it's been around since 2.0, but it itself is also being evolved. I'll say that from ARM's perspective, that's the way they are going. I think it's still very much early days for other vendors. Other vendors will probably start doing it if they see results from how end users appreciate that mechanism of delivery of IP information. I think even if you don't do all of the separation of configuration and implementation, just the fact that you have the constraints UPF delivered by the IP vendor is valuable in its own right. I don't think IP vendors are even giving you even a documented version of how to use the IP from a power perspective. So that giving you a constraints UPF, I think it's already a good thing in its own right, regardless of how you decide to refine it moving forward.
There's just one more question online. And would you recommend this for an internal IP flow?
Absolutely.
As well?
I would recommend it for an internal flow as well because it just allows you to do verification a lot earlier.
Good. Thanks, Gabriel. Thank you very much. Thank you.